Let us move into the most important part of our stereochemical discussion, which is optical activity. Any stereoisomer can have the ability to rotate the plane polarized light, and when it exhibits this property of rotating the plane polarized light, we call this phenomenon as optical activity. Now when we say optical activity, it involves so many factors and parameters. When we say that a particular molecule is optically active, then it should exhibit the phenomenon of optical activity. The phenomenon of optical activity involves the rotation of plane polarized light. Therefore, we need to understand what is light, what is plane polarized light, and why a molecule rotates a plane polarized light. So what exactly happens when light passes through an optically active compound, and also we need to ensure what are the criteria or what are the conditions that a molecule should possess to exhibit this phenomenon called optical activity. The phenomenon of rotating the plane polarized light by a molecule is called optical activity. The compounds exhibiting optical activity are called optical isomers. When a solution of known concentration of an optically active compound is placed in a polarimeter, polarimeter is the instrument that is used to measure the optical activity, and when the beam of plane polarized light is rotated through a certain degree towards the right, that is clockwise, then the molecule under investigation or the compound under investigation is called dextrorotatory. And if the compound rotates the plane polarized light to the left, which is anti-clockwise, it is called levorotatory. Dextro means right in Latin, levo means left. What is light? We all know that light is an electromagnetic radiation. It has both electrical and magnetic properties, and it has both electrical and magnetic vectors oscillating in a perpendicular direction. So when this light interacts with any matter, okay, the matter can be anything, it can be a solid, liquid or gas, and this interaction normally leads to several phenomena which we have studied in our lower standards in physics, namely reflection, refraction, resonance, and one such phenomenon is also called as birefringence. So this interaction leads to an array of phenomena, and the most common are reflection and refraction, which is also called as birefringence. Now, these properties depend on the type of matter, that is, the dielectric nature of the matter, and the properties of light such as color, which is again equivalent to frequency, and direction of propagation with respect to the material, and the polarization aspects. Now, any form of polarization depends on interaction between light and matter. So when there is an interaction between your light and matter, and if there is going to be a polarization, you know what is a polarization, which means separation of charge. So any form of polarization depends on the interaction of light and matter, and this phenomenon is what we call it as optical activity. So when light interacts with matter, there is going to be a change in the properties of that light, and that change in the properties of the light depends on the properties of the matter, and these two put together you call it as optical activity. So two types of optical activity can be observed when light interacts with matter. The two types are birefringence, also called as double refraction, and dichroism. So let us now understand that optical activity of a molecule is a combination of two important processes, namely circular birefringence and circular dichroism. So let us try to understand what are these two terms. These two terms are very fundamental terms, and we can define birefringence as the dependence of the speed of monochromatic light on polarization. Let us say that we are trying to pass a light through a medium, and a light can travel faster if the medium has a large amount of space. If the medium is enriched with atoms and molecules, then the velocity of the light will be disturbed, or in other words, the velocity of the light will be restricted. Now this leads to a polarization. What is circular birefringence? Now circular birefringence occurs when the speed of left and right circularly polarized light differ. We will look into what is this circular polarized light in a short while. But before that, let us try to understand that when the speed of the light is disturbed, or when the speed of the light is changed, then the phenomenon of birefringence occurs. Linear birefringence occurs when the speed of two orthogonal linearly polarized light beams differ. So circular birefringence is the most common phenomenon. See, we have already seen this circular birefringence kind of phenomenon in our lower classes in the process called Tyndall effect and Brownian motion. So the visibility of the molecules in the presence of light and those movements that we observe are actually as a result of that, what happens, the light, the speed of light, the velocity of light is disturbed. So circular birefringence is the most common phenomenon, and it gives rise to a rotation of the polarization plane of a linearly polarized light. So when light interacts with matter, not only its velocity is disturbed, but also its direction is also disturbed. On the other hand, the next phenomenon is called circular dichroism. Now, if there are certain molecules, atoms or groups in our compound, okay, say for example a carbonyl group is present in our molecule, and if light passes through this molecule, now this carbonyl group has the ability to absorb the light, because the carbonyl group contains pi electrons. It has non-bonding electrons. Now these pi electrons and non-bonding electrons can absorb radiation, and it can move to an excited state. So when this happens, the frequency of the incident radiation and the frequency of the radiation that is emitted out will differ. So we define dichroism as the dependence of the absorption or emission of monochromatic light on polarization. Okay, so circular dichroism that occurs when the absorption or emission of left and right circularly polarized light in matter differ, and linear dichroism occurs when the absorption or emission of two orthogonal linearly polarized light beams differ. So to conclude, if we send light inside a sample which is said to be optically active, both these phenomenon can occur. If the molecule is optically active, it can change the velocity of light, thereby resulting in circular birefringence. And if my optically active molecule has functional groups like carbonyl groups, it can absorb the incoming light, and it can give out a light with a different wavelength or different frequency, and that leads to circular dichroism. Both these phenomenon put together, circular birefringence and circular dichroism, is what we call it as optical activity. Let us take this example. So you can see we have an ordinary light. As I told you, a light is a electromagnetic radiation. But what is an ordinary light? An ordinary light will have its direction of vibration or direction of propagation in all directions, you can see. So this is the direction of propagation in all direction. Now when this light, which has its direction of propagation in all direction, that is an ordinary light or an unpolarized light, is passed through a linear polarizer. A polarizer is a material that can convert this ordinary light, unpolarized light, into a linearly polarized light. Okay, so when we pass this through a polarizer, and then you get a linearly polarized light, and once again when you pass this linearly polarized light into a quarter wave plate, okay, a quartz plate, okay, then the light that emerges out becomes a circularly polarized light. Okay, now you can see here, this is the direction of propagation of your ordinary light. You can see at one instance it is propagating in this direction, at one instance it is propagating in this direction, at one instance it is propagating in this direction. Now when this ordinary light is passed through a linear polarizer, now you can see the direction of propagation of light is restricted to only one plane. You can see there is only one plane, so you have only one plane. So this is what we call it as a plane polarized light. Now when this plane polarized light is passed through another quarter wave plate or another polarizer, then you get a circularly polarized light. Now you can see the direction of propagation is no longer linear, the direction of propagation becomes circular. So this is what is explained here exactly. So in a circularly polarized light, you can see the direction of propagation of two vectors, the electrical vector and the magnetic vector, moving in a circular direction. So let us have a close look about the plane polarized light and a circularly polarized light. Now we know that in any wave front, for example a light, okay, so it will have an upward motion and a downward motion, and this is how a wave propagates. Now the upward part is called a crest and the lowermost part is called a trough. The distance between two crest or a two trough is what we call it as a wavelength, and the maximum distance is what you call it as an amplitude. So these are all the properties of waves which you have already seen in your lower classes. Now what is exactly the composition of a circularly polarized light? If I take a circularly polarized light, it is a combination of two polarized light. So in the previous case, as I showed you, now this circularly polarized light is a combination of two polarized light. One is called a right circular polarized light and the other one is called left circularly polarized light. So you will have a right circularly polarized light. Please remember, your circularly polarized light has two components. One is right circularly polarized light, the other one is called a left circularly polarized light. Now when these two combines, okay, when these two combines, the net result will be like this. So when we say a circularly polarized light, it will be having a right circularly polarized light and a left circularly polarized light. Now when these two light interacts with matter, depending on the geometry of the matter, either the right circularly polarized light or left circularly polarized light will undergo a polarization, and thereby a circular birefringence occurs where the velocity of either the right circularly polarized light or left circularly polarized light changes. When this happens, then the net result, so see, when there is no change in the velocity of right circularly polarized light or left circularly polarized light is happening, the net result is the outcome, what you observe will be, there will not be any change in the direction of the outcoming light. But when your molecule is optically active, this circular birefringence occurs where any one, either your right or your left circularly polarized light's velocity is changed, thereby the net resultant vector may either appear to be moving towards right, or it may either appear to be moving towards left, because one of the circularly polarized light is its velocity is changed, either the RCPL or LCPL. Therefore, the net resultant vector that you observe at the end will have a different direction, and this is what we call it as a dextrorotatory or a levorotatory. Okay, so again coming back to the same diagram, you can see here. Okay, so you have an unpolarized light. Okay, and this unpolarized light is moving in two planes. Okay, you have an X plane and a Y plane, and when it is passed through a linear polarizer, you get a linearly polarized light, and when it is passed through a quarter wave plate, you get a left-handed circularly polarized light. So a quarter wave plate will give you only a left-handed circularly polarized. So if you have two quarter wave plates, then you may have both left and right-handed circularly polarized light. Okay. So what exactly happens when you have a molecule, an optically active medium, okay, and you are passing your light through this optically active medium, and you have a plane of polarization, that is a polarizer, and when your light, after passing through this optically active medium, if it is moving towards right, then that is the plane, if it move away from the plane of polarization, then you consider this molecule as dextrorotatory. So here we have taken the example of D-bromochlorofluoromethane. It's enantiomer, that is L-bromochlorofluoromethane, which is a non-superimposable mirror image. And if you pass the same light, okay, then you will observe the direction of the light changing towards the left, and you call it as levorotatory. What is specific rotation? Now, specific rotation is defined as the rotation produced by a solution of length 10 centimeter and a concentration, unit concentration of 1 gram per ml for the given wavelength of light at a given temperature. Now, this is the a simple experimental setup of a polarimeter. Here the sample is placed inside a compartment called sample compartment, and if that compartment can accommodate a solution whose and if this compartment length is only 10 centimeter, and if the concentration of the sample that we are going to use is only 1 gram per ml, then what we are measuring is not optical activity. What we are measuring is specific rotation. Okay, so when you pass light, you can see the light travels in a single direction, that is, it is a plane polarized light. But once it passes through the compartment and when it comes out, you can see its direction has changed. So you will have an analyzing filter that measures the change in the angle, and this change is called as alpha. So specific rotation is given the symbol alpha. So specific rotation alpha is equal to observed rotation, that is what you have observed, divided by length, okay, length in decimeter, and concentration. So concentration is nothing but a pure liquid in gram per solution, or a solution in gram per 100 ml of the solvent. So if we give all these values and if we find the specific rotation, and that specific rotation is considered to be the most accurate value for any stereoisomer. Another representation of what is exactly happening. So when the light passes through, when the normal light passes through a polarimeter, okay, and you can see the normal light becomes a plane polarized light. So we normally use a Nicol prism. Okay, Nicol prism is what you might have studied in your lower class. So a Nicol prism is used. So this Nicol prism has the ability to convert your normal light into a plane polarized light. And when this plane polarized light passes through the sample compartment that contains an optically active compound, molecular interaction takes place, polarization between the light and the molecule occurs, which results in the process of birefringence, circular birefringence and circular dichroism, that changes the velocity of the light, and as a result the net result would be the change in the direction of the outcoming light, or the outcoming light, or the light that comes out is change, its direction of that light changes by a specific value called alpha. Okay, and if everything is measured using a specific values, then you call this alpha as a specific rotation. So this is analyzed by an analyzer. So a change in rotation analyzed by an analyzer will give you the specific rotation of the molecule.